So today we're actually modeling geometric growth and decay. So again, geometric is whereby things are increasing at by a ratio. So we're multiplying by a ratio rather than a fixed amount, adding on or subtracting. We're multiplying by a ratio. Growth means it's going up. Decay obviously means it's going down. Now it says like linear growth and decay, it says geometric growth and decay are commonly seen around the world. Cool. Let's have a look at some examples. It says here some examples including the payment of compounding interest, or the depreciation of a value of a new vehicle by a constant percentage each year. This sort of depreciation is commonly called reducing balance depreciation. Okay, so again, when you hear the words reducing balance depreciation, we're using this particular method, geometric decay. It is different than straight line depreciation, which is the linear decay. Yep, so it's those words that you hear to decide which one we're going to be using. It says here a recursion model for geometric growth and decay. We've already had the chat about this, whereby we have a starting value, we have Vn plus 1 is equal to a ratio multiplied by Vn, likewise, you can also have, in this case, the initial value was 8, the next value is equal to 0.5 multiplied by Vn. And it shows, in this case, if you were to sketch it, and we've already had the chat about this, starting at 1, next value is 3 times the previous value. Again, you're going to get that curve going up, multiplying by 3. Here, where you're multiplying by a value between 0 and 1, so a fraction, it's going to be going down. And I've already also given you the heads up that if it's a negative value here, the graph is that seesaw type of thing, which they haven't spoken about yet. We'll look at later on down the track. There are some general rules where r is a constant. We've spoken about it. It can be greater than 1, and the value for r can be less than 1 to show geometric decay, so it's going down. Good. It says we're now in a position to use this knowledge and model, investigate compound interest loans, investments, and reducing balance depreciation. Cool. We've got the knowledge. It says compound interest investments and loans. It says most interest calculations are not straightforward as simple interest. So they are a little bit more complicated. Again, so where you hear compounding interest, it's getting added on more regularly. This is different than simple interest, and make sure you read the question carefully as to what we're doing. At the moment we're doing compounding interest. And what it means is, generally speaking, when you go to a bank and you are getting interest, generally it is compounding interest that is happening on loans. Basically, compounding interest is where any interest that is earned after one period of time is added to the principal and then contributes to the interest in the future, in the next period. It says this means that the value of the investment grows in every increasing amount or grows geometrically instead of by the same amount as in simple interest. So basically with simple interest, it's always the same amount that's going on. With the geometric investment, where it's compounding, it gets the new principal value and it's getting it's growing on that. So as it gets larger, more and more is happening. It's actually changing that interest amount over time. So it says here, consider an investment of $5,000, pays 8% interest per annum. Notice as well, it says it's compounding yearly. So as soon as you see the word compounding, we're using compounding formula. This means that the investment's value increases by 8% each year. Again, we can model this investment using recursion relations. Let Vn be the value of the investment after n years. And we can write the initial value. Textbook's wrong here. You can fix this up. V0 should actually be $5,000. Was the initial value. Change that to a 5. It says each year the investment will increase by 8%. So the next year's value is going to equal this year's value plus that interest that is earned. And so symbolically you would use this here. You can compress this down to this particular thing here. Let's actually have a look at it in reality. This is the bubble box that you need to be aware of. It says let Vn be the value of the investment after n years. We're cool with that. Let R be the percentage interest rate per compound period. Cool. We've spoken about this before. V0 is the starting value or the principal value. The formula for these geometric compounding questions is Vn plus 1 is equal to the ratio value multiplied by Vn. So the next value is equal to the ratio by the current value. What you do need to know, and I would highlight this, is how to get that R value. So the R value is 1 plus the interest rate as a percentage over 100. Yep. So if you were doing this question up here, where you had 8%, the R value is going to be 1 plus 8 over 100. 8 over 100 is 0.08. That's why up here it became 1.08, because the R value is 1 plus that percentage over 100. Yep. Wasn't clear actually up here, so hopefully it's become clearer as we look at this one and the example below. Alrighty, let's get stuck into it. What do we got here? Oh, cool. It's the following recursion relation can be used to model a compounding investment of $2,000 paying interest at a rate of 7.5% per annum. So again, writing out the recursion relationship using this information here. V0 is equal to the starting value. It was the principal value that you started off with was $2,000. V0 equals 2,000. People should be happy with that. Recursion relationship says Vn plus 1, so the next value is equal to R multiplied by Vn. Now, to work out what the R value is, big R, I'll refer to these as big R and little r. To work out big R, the ratio, it's 1 plus the interest rate over 100. So to work out big R, in this case, it's going to be 1 plus 7.5 over 100. 1 plus 7.5 over 100 is 1.075. That's where that comes from. Cool, so we've set up the recursion relationship there. Actually, they gave it to you, but I just explained it. It says in this recursion relationship, Vn is the value of the investment after n years. Cool. It says use the recursion relationship to find the value of the investment after 1, 2, and 3 years. Yep. So in this particular case, all you have to do is substitute in the values into where n is, and it will tell you what's happening after each of these years. So let's actually see what's going on. We've got the initial value. We're going to use the recursion relationship to calculate the values V1, V2, and V3. So V1 is going to be equal to 1.075 multiplied by the one before that, which was V0, which is 2,000. Yep. So we can get the it's $2,150 at the start. To calculate the second year, yep, we're going to be calculating V2. So that's going to be 1.075 multiplied by the one before that, which was obviously V1, which we calculated. We get that there. You can see going through that. I hope that you guys are pretty happy doing that. So after 3 years, you can see that it comes out to being $2,484.59. Cool. Now, one of the other things that you can do, it says here, determine when the value of the investment is going to be greater than or exceed $2,500. Okay, so what you can do for this is on your calculator, you press $2,000 is the amount that you're starting off with. Press enter or execute on your calculator, and it'll set it in there. We're going to then multiply that by 1.075. So as soon as you type multiply by 1.075, it'll do this. And what you're going to do is count how many times you keep on pressing that execute button. It will keep on multiplying the previous one by 1.75. Yep. And you should be able to find out, okay, we clicked it once, twice, 3 times, 4 times is the as it's come over $2,500. You can see here it's $2,670. So that's when it becomes greater than or exceeds $2,500. Yeah. So that's a nice little trick actually that the textbook's showing you to work out how many years it's going to be until it's greater than 2,500. So you're going to click it once, twice, 3 times, 4 times. So saying actually it's going to be 4 years because you have to click the button 4 times until the investment's going to be greater than or exceed $2,500. Cool, I like that. Next one, it says here, write down the recursion relation if $1,500 was invested at a compound interest rate of 6% per annum. Alrighty, so this is really where we need to start thinking about, okay, we need to write down the initial value, the principal value, V0. It's going to equal $1,500. And we know that the rate was 6%. Yep. Now, that's little r is the interest rate. Yep. We need to actually work out what big R is. Yep. So remember to calculate big R, it's 1 plus little r over 100. We said little r was 6. 1 plus 6 over 100 is 1.06. So from there, we've got big R, we've got V0. You can neatly write out the recursion relationship, yep, which you guys should be fairly happy doing. Cool, I like that example. Yep. All right, let's have a look at the next one. Oh, what's going on here? Oh, it's Brian. Brian, he's borrowed $5,000 from the bank, and it says he will pay interest at a rate of 4.5%. Actually, now, this says 4.5% on the computer. My textbook that's in front of me says 4.8%. I'm wondering which value they've actually used that's correct. I reckon they've made a mistake here. This should be 4.8%. Yep. So let me fix this up. Let me get my correction pen. That's not a correction pen. Sorry, guys. I'm wasting your time here. Correction pen 4.8. Fixed. Okay, that'll be an 8 there. 8 and so forth. Yep. So it says, sorry, that should be 4.8. Write down the recursion relationship in the model for the value of Brian's loan if the interest is compounded yearly, quarterly, or monthly. Now, this is really the point of the question, is showing that depending on when or how often the interest is compounded, it could be daily as well. Yep, it does make a difference to the calculations. Yep. So let's have a look at what happens when the interest is done or compounded yearly. So it says determine the value of R. It should be 1 plus 4.8 over 100. 4.8 over 100 is 1.045. We know the initial amount was 5,000, so writing out the recursion relationship would be as follows. Yep. It says, yeah, so that's compounded yearly. Yep. Perfect. Next, it's saying what happens if it's done quarterly. Okay, so same difference again. Now, in this example up here, it was because it was 4.8% per annum. Per annum means yearly. Yep. So that's why we're just using the value 4.8 to do this calculation here. And it's all happy for yearly. But notice if we have to do it quarterly, when you work out the interest, that should be 4.8. Sorry, guys. To work out the quarterly rate, you have to do the R value is 4.8, and that is divided by 4 because there's 4 quarters in a year. Yep. So you're actually going to have a little R value. It's not 4.8 that gets substituted in here because it's happening quarterly, 4 times a year. You have to divide that percentage per annum by 4, which becomes 1.125. From there, we can go and put it into the big R value. Happy days. We're all going to be okay. Last but not least, there should be no surprises. This one's saying, hey, what happens if it's monthly? Hopefully you realize that there's 12 months in a year. So if we've got the 4.8 is the yearly percentage, and they want it to happen monthly, we're going to have to divide this by, yep, you guessed it, 12, because there's 12 months in a year. So it would be 4.8% per annum. It's 4.8 for the year. We need to divide it by 12 because it's going to be monthly. so 0.375, and from there we can get the big R value using that. Yep. Cool. Now, really quickly, like we had with the increasing of investments and loans, you can also have the depreciation using reducing balance rather than the straight line method of depreciation. So this one's reducing balance. Again, there's a rule. You can happily read this here. I'd be highlighting this. Notice it's the same formula here, except with the rate, because it's decreasing. To find out what big R is, it's going to be 1 takeaway, little r over 100. Yep, so it's going to be decreasing, depreciating. Yeah, cool. So again, we'll quickly go through this example. It says the following recursion relationship can be used to model it's office furniture again. They purchased it principally for $6,900 as depreciating at a rate of 7% per annum. Cool. We can write out the recursion relationship. They've already given it to us. Happy days. It says use recursion relationship to find the value of the office furniture correct to the nearest centre after 1, 2 and 3 years. So again, we just need to substitute in these values here. When it's the first year, obviously we multiply 0.93 by the one before it, which was V0. We can do that for each of them to find out what's going on. Determining the value, when the value of the investment will be less than $5,000. Like we did before, type in the value to start off with, multiply it by the big R value, 0.93, press execute a few times until it gets to the value that you're after. So they want to find out when the number gets less than 5,000. Click once, twice, 3, 1, 2, 3, 4, 5. On the 5th click, it's less than the $5,000. Yep, so the value of the furniture will drop to less than $5,000 after 5 years. 1, 2, 3, 4, 5 years. Yep. It says write down the recursion relationship. If the furniture was initially valued at $7,500 and it depreciated using a reducing balance rate. Yep, not straight line, reducing balance, which is what we're doing in this exercise. Of 8.4% per annum. Cool, so I'd write down what V0 is, it's 7,500. I would write down what the little r value is, it's 8.4%. We can calculate big R using the formula above. It's depreciation, so remember it's 1 takeaway, little r over 100. We get that value. We can then write out the nice recursion relationship from there.